our library is growing. We've just been through another atomic test. For a military man, any one of us, the considerations, the problems of atomic warfare are better understood today than ever before. Military participation in Operation Tumbler Snapper is a matter of record. Experience to be used for military plans of both warfare and future atomic testing. The Nevada Proving Ground is beginning to be an old stomping ground for a lot of us in the services. On Tumbler Snapper, as on Buster Jangle back in the fall of 1951, headquarters in the forward area is a boom town called Camp Mercury, lying some 20 miles to the south of the test area. This is the place for living, working, and any recreation you are able to squeeze into a very busy schedule. The Armed Forces machine for atomic testing was better oiled than ever before. Every element of that machine ran a good many long, hard hours, hot days, and cold nights to meet a rigid schedule of nuclear detonations. If you've ever been on an atomic test before, either here in Nevada or overseas at Eniwetok, chances are you've made a good many friendships with people you see only once or twice a year. It's a big fraternity, this order of the mushroom, and it's growing all the time, as more and more of us from all the services have an opportunity to be a part of this big effort to collect the know-how for atomic warfare. We're still on the ground floor, but the ground floor is getting a little higher on every operation. There's no such thing as a normal working day on an atomic test. The labor pains continue around the clock until the job is done. Because AFSWAP, the Armed Forces Special Weapons Project, is the joint service agency that plans and coordinates all of the military effects tests that are run on an operation of this kind, a special command, a test command, was created. Tumbler Snapper, as Buster Jangle, was a combination weapons development and military effect test. A total of 8 nuclear weapons were detonated. Most of the military tests were run on the first 4 shots, the tumbler phase of the operation, consisting of 4 daylight airdrops. However, the 4th tumbler shot did play a part in the AEC weapon development program. The snapper phase of the operation comprised the last 4 shots. The weapons themselves were installed in 300-foot towers and fired during the hours of darkness. Snapper was almost exclusively devoted to AEC weapons development. Since comparatively few military tests were conducted on Snapper, let's take a quick look at that phase first, before we get into the heart of our story. At this moment, the installation of a test weapon is being completed in the first zero-tower cab. In the study of new weapons, like those on the Snapper phase, much depends on instrumentation in close proximity to the bomb itself. The internal workings, as well as the external effects of the weapon, are studied and cross-checked in many ways. The events taking place inside the bomb occur with extreme rapidity, in millionths of a second. An instrument located near the bomb in the cab of the tower must be able to work fast enough and capture enough data to accurately analyze the bomb's functioning before being destroyed. The record of the weapon's behavior, recorded in a millionth of a second before it flies to pieces, is sent back down the coaxial cable from detecting instruments in the cab to a recording station several thousand feet away. The weapon is in position and the firing circuits checked out, ready now for firing from a control panel back at the CP. The underlying philosophy behind the entire weapon development program is to realize the maximum kiloton yield from the fissionable material involved. In other words, obtain the highest degree of efficiency. However, equally important is the continuing development of different weapon types to provide complete flexibility in delivery methods and techniques. At the CP, scientific and military directors wait out the final few hours. Everything is in place. Everything is ready at the Nevada Proving Ground. From now until H hour, the entire test site, all operations, the detonation of an atomic weapon over the Nevada desert, pivots around one focal point: the fortunes of weather. Here in sequence are the 4 Snapper blasts, detonated atop their steel towers on the 7th and 25th of May and the 1st and 5th of June. The weapon ideas being proof tested on Snapper involve weapons of a smaller physical size that might be carried externally on fighter-type aircraft in tactical air support of ground operations. Every nuclear detonation is followed up by the priority operation of collecting samples of the unburned fissionable material and bomb debris. Atomic cloud sampling with jet aircraft, an idea tried on Buster Jangle for the first time, is standard operating procedure on Tumbler Snapper. The jets can get the required samples faster and with less personnel exposure. 2 men ride in the sampler aircraft: a pilot to fly the airplane and a radiological safety man to help him locate and penetrate the hot spots in the cloud where the required samples can be gathered. The planes themselves are radiologically hot, very hot, because the skin of the airplane has collected bomb debris too. The problems of working with high levels of radioactivity are pretty well understood by this time. The safety precautions have been proven and defined in the course of literally dozens of cloud sampling sorties on previous atomic tests. The approach is realistic. The hazards are understood thoroughly. The cloud samples themselves are collected in wing-tip sniffers, specially designed tanks suspended from each wing. Inside the sniffers, chemically pure paper filters are installed to latch onto and hold particles of bomb debris the plane encounters in its passes through the cloud. The operations are simple and literally eliminate the possibility of any serious personnel radiological contamination. All post-blast recovery of sample papers, as well as decontamination of the planes, will take place here, at a safe distance from the flight line. The jets will be ready for operation in about 24 hours from now. Once the sample paper from the sniffer is removed, it is placed in a lead coffin for safe transport to Los Alamos and complete radiochemical analysis. Well, that gives you an idea of the Snapper phase of the operation, of military interest in the weapons development program. Those of us in the armed forces ran almost all of our tests on the airdrops, the first 4 shots of the operation, the Tumbler phase. On Tumbler, we had to get the answer to what was perhaps the most important military question with respect to the effects of atomic weapons since the proof test of the first bomb at Alamogordo. Back in about 1948, a series of curves were prepared on blast pressures versus distance for different heights of burst and different yields of bombs. All our offensive and defensive plans incorporating or considering atomic weapons were based on these curves. These curves are wrong. The error is severe according to more complete data collected on later atomic tests. Diagrammatically, an atomic detonation looks like this. 4 effects are produced: light, heat, radiation, and blast or air pressure. Since blast is the primary destruction force of the bomb, let's take a closer look at the blast portion of the event. The bomb is detonated in relatively cold air. The pressure wave produced by the energy released moves faster than the speed of sound in all directions at the same time, in what is known as the incident shock wave. The air is heated by the sudden compression caused by the shock wave. As the incident wave strikes the ground, most of the energy bounces back in a reflected wave. The resultant peak pressure in the reflected wave is about double the pressure in the incident wave, thereby doubling the destructive power of the shock force, or front, moving across the ground. Because the air behind the incident wave is hot, the reflected wave can move faster and gradually compress the base portion of the incident wave into a wall or stem of boosted air pressure, called a Mach Y stem. On a graph, the event looks like this. The greatest pressure, of course, is produced at ground zero by the combination of the incident and reflected waves. The pressure gradually drops off as the waves move out from ground zero until the Mach Y develops and increases the pressure again. It was this amplification which extended the area of damage at Hiroshima and Nagasaki. The Mach Y stem worked over every type of structure: masonry, steel frame buildings, reinforced frame buildings. From a military standpoint, the atomic detonations on Japan seemed to be pretty effective. So Hiroshima and Nagasaki became the norm, the basis for curves on blast effects and damage. During Bikini in 1946, damage to ships in the lagoon and equipment on the beach agreed with blast damage curves developed in Japan. Theoretical height of burst curves were developed from effects observed during Hiroshima and Nagasaki, the Able shot at Bikini, and were backed up by high explosive experiments. During Operation Greenhouse at Eniwetok in 1951, men from each of the services got their heads together and dreamed up the most extensive blast study program up to that date. It involved every principal type of structure, many above, some below the ground, in a variety of orientations to the burst. It involved airplanes in the sky, parts of airplane structures on the ground, tanks, and other types of military equipment. The pre-blast estimates of damage were based on composite blast curves developed from studies of Japan and theoretical calculations. Pressures resulting from the tower shots of Greenhouse were less in some cases by a factor of as much as 2/3 than the original predictions. On the bursts of Buster Jangle, even more severe differences showed up between the predicted blast effect estimates and the actual results produced by nuclear weapons. For unknown reasons, nuclear weapons were producing, in some cases, only about 1/3 the blast pressure that we had expected. This raised some very sobering questions in the minds of military planners. We knew the energy was there, but something somewhere along the line was happening to lessen or cushion the full effect of the blast. Where and why are there such discrepancies in our blast curves? Getting the answers was our priority objective.